Okay, now we're solving question number 5. Let's see which seemingly is a question about moments. Let's see what it says. A beam AB has mass 30 kg and length 3 meters. All right. The beam rests on support C and D where AC is equals to 0.4, DB is equals to 0.4 as well. A person of mass 55 kg stands on a beam between C and D. All right. And then the question says that the person is modeled as a particle at the point P, okay, where Cp is equals to x meters, okay, and also x is between 0 and 2.2. Okay, so this is something that will definitely come in handy. We'll see that in the later parts. Then the question says the beam is modeled as a uniform rod resting in equilibrium in a horizontal position. Using the model, show that the magnitude of the reaction at C is 686 minus 245x Newton. Okay, so there's a lot going on in this question. So let's read the question again and let's try and connect the dots. So first of all, we're given the mass of the beam to be equal to 30 kg and the person is standing at P. Okay. And also it's in equilibrium. So a good idea would be, because I believe there are multiple parts. Yep, there are 3 parts. So let's take a picture of this. Yeah, and let's paste it here. Now it's in equilibrium. Okay, according to the question, it is in equilibrium. Now if it's in equilibrium, that means since the rod is uniform, there is a force of 30G acting downwards. Okay. And there is a force of 55G, the person, acting downwards also. Now, what are the two forces, or what are the all the forces that are acting in the opposite direction, which is what is basically keeping this in equilibrium? These are the reaction forces. So because the rod is, this is the point of contact, so there's got to be a reaction force. So since the point of contact is C, we're going to write this as the reaction force at C, and this here, the point of contact is D, so we're going to write this as a reaction force at D. Okay, now what are we supposed to do? Let's keep our eyes on the prize. We're supposed to show that the magnitude of the reaction at C is equal to so and so. Now, magnitude of reaction at C. So if I calculate the moment about C, that's not going to help because then we won't have C in the equation. Okay, so we'll have to pick a point about which we calculate moment so that there is no C into the equation, and that is basically D. So the moment that we will calculate will be about D. And why are we doing so? And when we do that, what's the assumption? The assumption is that all the clockwise moments are equal to all the anti-clockwise moments. Okay, so since we don't have a lot of space, let's try and be as efficient as possible. Now, a good idea would be to first find out all the distances that we will need. So we're given this distance, since we're calculating moments about D. So this distance would be equal to 1.5, since this is from the center of the rod or beam, whatever it is, 1.5. So that means this distance would be 1.1. Okay. And this distance would be, let's have a look. This distance would be 2.2 minus x. Now, why is that? Let me show you. So this distance would be 2.2. Why? Because this is 3. So from 3, we will get rid of 0.4 and 0.4. So this is 2.2. This is x right here. So this would be 2.2 minus x. Let's write that down. Okay, anything else that we need? Actually, we don't need 2.2. Yeah, we need 2.2 minus x, and this distance would be 2.2. Yeah, so this distance right here would be 2.2. Okay, and why will this be 2.2? This is 3. From 3, we get rid of 0.4 on both sides, and we're down to 2.2. Okay, I think we have enough information. So remember, all the clockwise moments will be equal to the anti-clockwise moments. So let's first look at all the clockwise moments. So this is clockwise. Okay, I don't think there is any other clockwise moment. Then now we have anti-clockwise moments. So that would be this 55G and this 30G. Okay, so let's start with clockwise moments. No, wait a minute. This would be, this would be clockwise. Okay. So the reaction at C multiplied by the perpendicular distance from D, since all the moments are being calculated about D, that would be 2.2. Yeah, so RC into 2.2 is equal to all the anticlockwise moments. So 55G multiplied by how far away is 55G from this? This is 2.2 minus X. We worked it out over here. So 55G into 2.2 minus X plus 30G. Now, how far away is the 30? Is this force from the point that we've taken into consideration? That's 1.1. So 30G into 1.1. Now, we will be solving for RC. Okay, that's what we're solving for. So let's work it out. So 55G, let's keep our eyes on the price also. 55G into 2.2. So I'll try and keep G as it is for now. So 55 into 2.2, that's equal to 121G minus 55G along with X. Okay, plus 30G into 1.1. So 30 into 1.1, that's equal to 33. Okay, and what is this equal to? This is equal to RC times 2.2. Okay, so this can be subtracted. Don't forget the G here. No, actually, not this. This can be subtracted. 121 minus 33. Let's work that out. 121 minus, will it be minus? Will it be plus? 121 plus 33. That's equal to 154. So what do we have? We have RC times 2.2 is equals to 154 minus 55 GX. And how are we supposed to write it? Okay. So 154, don't forget G with 154, 154 G. So now let's multiply 154 and 55 with G. So RC into 2.2 is equals to 154 times 9.8. Remember, G is equals to 9.8 meter per second square. So that's equal to 1509.2 minus 55 into 9.8. That's equal to 539x. Now we calculate RC, which would be 1509.2 minus 539x divided by 2.2. So let's divide both these values by 2.2. If you've done it correctly, we should get what the question mentioned earlier. 1509.2 divided by 2.2, that's equal to 686. So looking good so far. 539 divided by 2.2, that's equal to 245 along with X. Is this what we were supposed to get? Yep, this is exactly what we were supposed to get, and this is the correct answer and also the end of the first part. Okay, so I'll give you a bit of a summary. So the rod was in equilibrium, the beam, or is it a beam? Is it a rod? What is it? It's a beam. Yeah, so the beam was in equilibrium. That means there are two forces acting downwards. One, obviously, its own weight, and there was a person standing at B. And since it's in equilibrium, that means all the forces acting downwards will be equal to all the forces acting upwards. Okay. Now, if that is the case, so what we're supposed to do is we're supposed to calculate the reaction at C. Yeah, we're supposed to calculate the magnitude of the reaction at C. We're not supposed to calculate, we're supposed to show that this is what it's equal to. So I have to make an equation which only has RC and has no RT. So what better way to do that than to calculate moments about D? Okay, so we see how far C is from D, we take the moment multiplied by we take the force multiplied by distance, and we do that with all the anti-clockwise forces, 55G multiplied by distance. So make sure you spend a decent amount of time first working out all the distances before you proceed further, because you're going to need these distances in the later parts also. Okay, so that's it. That's the answer to part A. Now let's have a look at part B. So let's do part B here. So part B says, here is part B. Yeah. The magnitude of the reaction at C is 4 times the magnitude of the reaction at D. Okay, so let's make an equation. The magnitude of the reaction at C is equals to 4 times the magnitude of the reaction at D. Okay. And looking at all the forces, we know that this force plus this force is equal to the sum of all the reaction forces at C and D respectively. So that means RC plus RD is equals to 55G plus 30G. Okay, so that means RC plus RD is equals to 85G. Now, notice that we have two unknowns over here. So we can actually say that this is equation number 1, and we can say that this is equation number 2. And what we can do is we can actually solve them simultaneously. Yeah, that's exactly what we're going to do. We're going to solve them simultaneously. So since we already know what RC is equals to, RC is equals to this. So we're going to solve for RC and then we're going to replace it over here, which will then help us find out the value of X. So if I want an equation which I can solve for the value of RC, that means I will have to make RD the subject using the first equation, which would be equal to 1 upon 4 RC. Okay, so this has come with the help of the first equation, and this is now going to be substituted into the second equation. So RC as it is, plus 1/4 of RC is equals to 85G. RC plus 1/4 of RC, that would be equal to 5 upon 4 RC. Okay, you can use your calculator. Just do 1 plus 1 upon 4 is equals to 85G. Okay, let's make RC the subject. RC would be equal to 85 times 4 divided by 5. That's equal to 68G. Okay, so this is what RC is equal to. And what is RC equal to? RC is equal to 686 minus 245x, which is now we know is equal to 68G. Okay, so let's solve for the value of X. So 686 minus 68 into 9.8, sorry. Okay, so we are looking at 19.6 is equals to 245x. Okay, and then let's solve for the value of X. So divided by 245, so we have the value of X, which is equal to 0.08, and that is the correct answer. Okay, so so basically this was the one piece of information that we wanted. And obviously this we figured out earlier because it was an equilibrium, and we put these two together, and we used whatever RC was that we expressed earlier in the previous part, and we solved for the value of X. So that's part B. Now let's have a look at part C. So here's part C. Let's see what it says. So a good idea would be to first actually take a picture of it. Now, so let's solve it here. Part C says the person steps off the beam and places a package of mass m kg at A. So a good idea would be to copy this also and paste it here. Okay, so that means the 55G force will no longer be there because the person, as mentioned in the question, has stepped off the beam. Okay, and instead we have a mass of m kg at A. So that means now there is a force of mg acting downwards from A. The package is modeled as a particle at the point A. All right, the beam is now on the point of tilting about C. Okay, so the beam is now on the point of tilting about C. Using the model, find the value of m. Okay, so it's on the point of tilting, it's not tilting. So that means we can calculate moment, and anti-clockwise moment will be equal to clockwise moment, and we can use that. Okay, so this p is no longer there, by the way. We can use that to calculate the value of m. So let's calculate the moment about C. Okay, so the only anti-clockwise moment is this, and this now becomes the clockwise moment. Now we will obviously have to find out the distance. We figured that this, okay, let's see what this would be equal to. So this would be equal to 1.5, okay, because it's from the end to the halfway mark of the beam, so that's 1.5. Okay, and this is equal to 0.4 as mentioned, so that means this would be equal to 1.1, and okay, wait a minute, yeah, this would be equal to 1.1. Yeah, this would be equal to 1.1. Okay, I was wondering maybe we have to use x here, but no, we don't. This is equal to 1.1. Okay, great. So anti-clockwise equals to clockwise, and the only anti-clockwise moment that we have is mg. Okay, and this would be equal to the clockwise moment. So mg multiplied by the distance, so that's 0.4, is equals to the clockwise moment, which is basically the force, the mass of the rod multiplied by acceleration due to gravity, which I believe is 30. Yeah, so 30g. So 30g multiplied by the perpendicular distance from C, which we can see is 1.1. So 30g into 1.1. Let's see what do we have. So we have 0.4 mg is equals to 33g. So we have g on both sides. That cancels. Let's find out the value of m, for which we will do 33 divided by 0.4, which is equal to wait a minute, 30 into 30 into 1.1, that's equal to 33. Yeah, everything looks good. 33 divided by 0.4, that's equal to 82.5. And there you go. That is the answer to part C and also the end of this question.